Hello, students. Today we're going to talk about audition, which is a fancy way of saying your sense of hearing. Audition. So the first thing you have to understand is that our ears have developed over a long period of time. They've evolved to detect changes in air pressure, tiny little vibrations, which is pretty neat when you think about it. So when we talk about sound, it's important to know that when we look at sound waves, the taller or the higher the amplitude, the louder the sound, and the smaller or shorter the amplitude, the quieter the sound. Conversely, when we talk about frequency, the lower the frequency or the distance between the tops of the waves indicates a lower pitched sound, so something bassier, and then something that is higher pitched has a higher frequency, or so the wavelengths are closer together. It's also important to note that we hear up to about 20,000 hertz. Depending on your age, that's going to have declined a little bit, but that's the general frequency of human hearing. But there are sounds that are outside of our range of hearing as well. So for me, I'm the kind of person that needs to see this stuff in order for it to make sense. So I thought I would do just that for you. So if we look at here we have a sound wave. Now notice the wave isn't moving because there is no sound yet. So first we're going to look at a low frequency wave. So when I press this key, notice how the wavelength works. The amplitude, which is the height of the wave, you can see the frequency, that's low frequency. Okay, so now let's look at a higher pitched frequency and notice the difference in the way that the wavelength looks. It's closer together, almost where you can't see the perfect wave shapes. Let's go down just a little bit. We'll go middle C here. So notice it's a higher frequency wave than the lowest one. And I can't adjust the amplitude so you can't see, but if it was a louder sound, the wavelength would actually be taller. If you're a fan of electronic music or synthesized music in any way, shape, or form, wavelengths actually look different, and different shaped wavelengths make different sounds. So we're going to look at a couple of different ones, different oscillators. So the first one we're going to look at is a square wave. So notice you're going to look at the mouth of this weird square monster here. See the square shape? Now look what happens when I make the frequency lower. See how it vibrates slower now? Now let's make it a higher frequency. Notice how much faster the wavelength vibrates. Okay, let's take a look at, this is called a sawtooth wave. So again, it's called a sawtooth because of basically the shape of the wave looks like the teeth of a saw. Okay, and then if we make it higher pitch. Okay, and let's take a look at a triangle wave. And a sine wave. So sine wave's close to the wave shape that we looked at just a minute ago. And that is it for our different wave shapes. I hope that helps you to better understand the variation in amplitude and frequency and even shape changes the sound that you are perceiving. Place theory. So place theory basically states that wherever the place on the cochlea where the tiny hair follicles are stimulated determines the frequency that we're hearing. So the closer we are to the beginning of the cochlea, we're hearing the higher pitched frequency sounds. But as you go, further through here, and you get towards the sort of apex of the cochlea, that's where you're hearing the really low frequency sounds. And generally speaking, hearing loss, like just gradual hearing loss over time, occurs when we lose the ability to perceive sound and the higher registers or higher frequencies. And so it tends to be higher pitched sounds go away first, and then lower frequencies are the last to go. Frequency theory is basically just what I kind of talked about. So each of your ears is receiving a different, slightly different sound. So this allows us to detect like where sound is coming from. And then it's basically like the position on our auditory nerve where that's stimulated. I'm not going to ask you to know frequency theory, but it's just kind of interesting. You can Google it if you want to know more. So yeah, and the Volley principle is basically what I just talked about. So our auditory system responds to, they're slightly, the different sounds each of our ears hear are slightly out of phase, but when our brain combines them, it's encoded so our brain can be analyzed. And again, this is another thing that I'm not going to ask you to know about, but I think is interesting. Now let's look at ear anatomy. So I'm going to go very briefly over ear anatomy, and then I'm going to have you guys watch a video, which I think does a better job of showing exactly the process of how sound gets from your outer ear to your brain. So the ear is divided into three parts. There's the outer ear, the middle ear, and the inner ear. The outer ear consists of what's called your pinna. That's the flappy thing that you see on the sides of people's heads. Your ear and your ear canal as well. So basically the pinna, like you can do this right now. If you cup your hand over your ear, you're creating a larger pinna to allow more sound to be funneled into your ear. So that sound kind of vibrates inside of your ear canal, which stimulates the eardrum, or the tympanic membrane, makes it vibrate. And then it has the tiniest bones in your body, the ossicles, malleus, inus, and stapes, which attach to the cochlea. So we looked at the cochlea a little bit earlier. So the cochlea is actually one of the hardest bones in your body. And it's this, like, it looks kind of like a snail shell here. And it's a fluid-filled bone that has these tiny hair follicles inside of it called cilia. And the cilia are kind of like waves of grass. If you've ever seen a field where the grass is sort of waving in the wind, it's kind of like that. And they're working right now to listen to what I'm saying. So those cilia move back and forth, and this sends out little action potentials, little messages that travel via the auditory nerve off to the auditory cortex, which is located in the temporal lobe of the brain. Anyway, let's go ahead and watch that video now. Hearing loss. So there's a couple of different types of hearing loss. Conductive hearing loss occurs when there's something obstructing or there's an abnormality which is preventing hearing. Often this can be corrected with medical intervention. Sensory neural hearing loss occurs when the cilia inside of the cochlea are damaged or die. This can happen in regards to like getting older, or being exposed to loud sounds. There's currently no treatment for sensory neural hearing loss. So I thought we'd end today by showing you a video of a mishap that occurred with the rock band The Who, which left their guitar player permanently deaf in one ear. And that's all I have for you today. If you have any questions, let me know. Otherwise, have a fantastic day.